Greetings everyone, and welcome to the next video in my lecture series on differential equations. We're still working on Laplace transforms, and in this video we are doing examples of translations on the s-axis. So for our third example, we're going to find the following inverse Laplace transform. The inverse Laplace transform of 2s plus 1 over s squared minus 6s plus 25. So we take a look at the denominator and we notice that we cannot factor it. So we're going to complete the square. We get that s squared minus 6x s plus 25. I'm trying to make my 5s nice and exaggerated so they don't look like my s's. That's going to be s squared minus 6s plus blank plus 25 minus blank. Adding and subtracting the same thing leaves our expression unchanged. So to make the thing inside the brackets equal to a perfect square, we divide the negative 6 by 2 to get negative 3 and square it. So we're going to be adding and subtracting 9. And so we're going to get that this is s minus 3 all squared plus 25 minus 9, which is 16. That means that our Laplace transform is equal to, or inverse Laplace transform is equal to the inverse of 2s plus 1 over s minus 3 squared plus 16. Now we've got some work to do because this doesn't look like isn't in the exact form of any of our Laplace transforms on our Laplace transform table. So we're going to first recall that the inverse Laplace transform of s over s squared plus omega squared is equal to cosine of omega t, that the Laplace transform of omega over s squared plus omega squared is equal to sine omega t. And so what we really want is to have a fraction that sort of looks like some constant a onto s minus 3 squared over s minus 3 squared plus omega squared to look like the cosine term. And then to make the remainder look like the sine term, we're going to have some constant b times omega to make this omega look like that omega. Okay, so that's the plan. So let's do a little bit of work here. We're going to say that I'm going to split this up into, we're going to take the Laplace transform. And what we actually want is, instead of 2s, we want 2s minus 3 plus 1. And now we have to add an extra factor, because what we've actually done here is we had 2s before, and now we've subtracted 6. So we're going to add a 6 so that we've in effect added 0 over s minus 3 squared plus 16. So if you multiply it out, you get 2s minus 3. 2 onto s minus 3 gives 2s minus 6, plus 1 plus 6 gives us the 2s plus 1 that we started with, up one step higher. Let's close our bracket here. And so just simplifying a bit, we get the inverse Laplace transform of 2 onto s minus 3 plus 7 over s minus 3 squared plus 16. And now I'm going to split this into two terms. We're going to get 2 onto the inverse Laplace transform of s minus 3 over s minus 3 squared plus 4 squared, or you could leave that as 16 if you wanted to, plus and then a Laplace transform, inverse Laplace transform of something over s minus 3 squared plus 4 squared. And a reminder, what we actually want in the numerator is a 4 to make it look like the omega that we had earlier. But the factor out front that we actually see should be a 7. So in order to make all of this work, I'm going to take the 7 out front and divide it by 4, so that when I take the 4 on the outside, this 4 here, and multiply by the 4 on the inside, then I get the 7 that I started with. And now we've got everything in the form that we want. So the first term is going to be 2. The s minus 3 is going to give us an e to the 3t term. And then we've got a cosine of 4t. And then the second term here is 7/4. And then the s minus 3 again gives us an e to the 3t term. And we have sine of 4t. For our fourth example, we're going to find the Laplace, inverse Laplace transform of 4s plus 7 over s minus 2 to the 8th power. And there's a couple of different methods that you can take from here to get this into the form of something we recognize from our Laplace transforms table. Method number 1, partial fractions. I do not recommend this method for the reason that you'll see immediately, which is if I try to take 4s minus 7 over s minus 2 to the 8th power, you can see that the partial fraction expansion is horrible. It's a over s minus 2 plus b over s minus 2 squared. Then you're going to have a c over s minus 2 cubed. And you're going to have an awful lot of terms, and this is just terrible. So what we're going to do is we're going to be a little bit more thoughtful about this. And for method number 2, there's an algebraic trick. Which is that we take our 4s plus 7 divided by s minus 2 to the 8th. And we're going to rewrite the numerator. It's 4s plus 7. But what I really want inside the brackets is an s minus 2. And if you multiply that by 4, what we've done is we've subtracted 8. So I'm going to add an 8 to the outside to balance, to make sure that I have what I started with, s minus 2's to the 8th. And if you want to check your work, just multiply out 4 into s minus 2 is 4s minus 8, plus 7 plus 8 gives us our 4s plus 7 that we started with. And then we split this into two fractions. We're going to have 4 onto s minus 2 divided by s minus 2 to the 8th plus 15 over s minus 2 to the 8th. And then the first fraction simplifies to 4 over s minus 2 to the 7. And then we have 15 over s minus 2 to the 8th, which is an awful lot better than the horrible partial fractions method. So just partitioning that off, let's recall what we're trying to get. We're trying to find the inverse Laplace transform of 4s plus 7 over s minus 2 all to the 8th power. That is equal to the inverse Laplace transform of 4 over s minus 2 to the 7th plus 15 over s minus 2 to the 8th. And of course, what we want is we want to rewrite it so that inside the bracket we have exactly the form that we would have on our table. We want s minus 2 to the 7th. That would be our n plus 1. So we want a 6 factorial out front. So the factor of 4 that we get from the numerator is going to be divided by 6 factorial, so that when we multiply all that through, we get what we started with. And then we're going to do the same thing for the second term. We're going to have 15 times the inverse Laplace transform of, we've got s minus 2 to the 8th power, so it's n plus 1, sorry. And so we want n factorial, or 7 factorial in the numerator, so we're going to take our 15 and divide by 7 factorial. This then gives us 4 over 6 factorial, and the s minus 2 gives us an e to the 2t term, and the 6 factorial over the shifted s to the 7th gives us a t to the 6th, plus 15 over 7 factorial, e to the 2t, once again from the shift, and we're going to have a t to the 7th term. And honestly, I think, consider that to be a fine answer, but if you prefer to grind out the numbers, it's 1 over 180, e to the 2t, t to the 6, plus 1 over 336, e to the 2t, t to the 7. And honestly, I think either of those is fine.